Hi everyone. Today we'll be looking at how to configure G-SRv6. SRv6 has received widespread industry attention. Given that the SRH introduces a high overhead in packet forwarding, multiple SRv6 SRH compression solutions have been proposed. Huawei's SRH compression solution is compatible with SRv6. It supports hybrid orchestration of compressed SIDs and traditional SRv6 SIDs, enabling SRv6 evolution from non-compression to compression. As such, Huawei calls its solution Generalized SRv6, or G-SRv6 for short. Let's use BGP L3VPNv4 over SRv6 TE policy as an example to see how to configure G-SRv6. In this example, a bidirectional SRv6 TE policy is established between PE1 and PE2 to carry BGP L3VPNv4 services. This enables CE1 and CE2 to communicate through the SRv6 TE policy. Next, let's look at the G-SRv6 configuration steps in a BGP L3VPNv4 over SRv6 TE policy scenario. The configuration procedure is similar to that in an SRv6 TE policy scenario, except for steps 2 and 3. In this video, we'll focus on the configuration in a G-SRv6 TE policy scenario. The configuration in an SRv6 TE policy scenario is described in a previous video. G-SRv6 supports both 16-bit and 32-bit compression. This video uses 32-bit compression as an example. First of all, plan or configure IPv6 addresses for interfaces according to the networking. Then, configure is, which involves global configuration and interface-specific configuration. Moving on, let's see how to configure basic G-SRv6 functions. First, enable SRv6 globally on the involved device. Second, configure a source address for IPv6 packet encapsulation. Using the IPv6 address of a loopback interface is recommended. Finally, configure a locator and opcode. Locators are routable and therefore must be unique in an SRv6 domain. It is recommended that the fixed prefixes of SRv6 locator addresses be the same. This makes it possible to compress more consecutive SIDs, improving compression efficiency. Unlike common SRv6 scenarios, compression scenarios require you to specify the compress keyword in the locator and opcode commands to indicate the use of GSIDs in SRH encapsulation. In addition, the COC flavor defined for G-SRv6 is configured on P1 and P2. After receiving a SID with the COC flavor, a node needs to update the destination address DA field with the next 32-bit GSID in the segment list. A GSID consists of multiple parts. The lengths of the block, compression static, and static parts correspond to those configured in the locator command. The node ID part is 16 bits long, which is obtained by subtracting the block length of 48 bits from the locator length of 64 bits. In 32-bit compression scenarios, the total length of the node ID and compression function parts is 32 bits. Because the node ID length is 16 bits and the compress static parameter is set to 8 in the locator command, the length of the compression dynamic part is 8 bits. The length of the args part in this GSID is 0 due to the args parameter not being configured in the locator command. Given that the total length of a complete SID is 128 bits, the remaining 16 bits are used for the dynamic part. A compression static opcode needs to be configured within the range of the compression static part. Based on the opcode and the configured locator information, we can then obtain a compressed end SID. After completing the earlier configuration and analysis, run the display segment routing IPv6 local SID end forwarding command to check the GSID information, which is consistent with the analysis result. In the command output, the value of the SID compress field is yes, indicating that the SID is a GSID. In terms of 32-bit compression, the block length needs to be an integer multiple of 4 with a maximum length of 88 bits. In terms of 16-bit compression, the block length needs to be an integer multiple of 4 with a maximum length of 76 bits. It is recommended that the length be an integer multiple of 16 and be as short as possible to improve 16-bit compression efficiency. During address planning, consider the evolution of compression solutions. It is recommended that the network be deployed according to 16-bit compression requirements. To ensure compatibility with 16-bit compression, you are advised to set the lengths of both the node ID and compression function parts to 16 bits. Next, you need to run the segment routing IPv6 locator command in the is process view to enable SRv6, enable is to advertise locator routes, and enable is to dynamically generate SRv6 end and end.x SIDs. If SRv6 SIDs are not statically configured, is can dynamically generate such SIDs. In this case, you can configure the auto SID disable parameter to disable dynamic SID generation. After completing basic G-SRv6 configuration and route advertisement, check information about device routes, including subnet and G-SRv6 locator routes. Now, let's see how to configure a G-SRv6 TE policy. First, create a segment list and configure an explicit path on each PE as planned. This involves specifying the end SIDs of P1, P2, and PE2 in sequence on PE1, and specifying the end SIDs of P2, P1, and PE1 in sequence on PE2. Because other devices may be added to the network in future networking expansion, it is good practice to specify SID indexes with a certain gap between each other. Doing so facilitates the insertion of new SIDs in the future. Then, create an SRv6 TE policy and set its endpoint and color. Ensure that the endpoint value is the loopback address of the endpoint node. Finally, create a candidate path in the SRv6 TE policy and configure the candidate path to reference the segment list created earlier. In contrast to SRv6 TE policy configuration, G-SRv6 TE policy configuration involves the following two key points. First, the compress keyword is added to the index command to indicate the use of compression information. Second, the block length configured in the index command must be the same as that configured in the locator command. To verify the G-SRv6 TE policy configuration, run the display SRv6 TE policy command. The command output includes color, endpoint, and SID information, which corresponds to the previously configured G-SRv6 TE policy information. The highlighted SID part shows GSIDs and their parameters. The value of compress flavor is not displayed as COC for the last GSID. In the case of 32-bit compression, the value of compress length is fixed at 32. After configuring the G-SRv6 TE policy, you can run the ping SRv6 TE policy command to check its connectivity. Alternatively, run the tracert command to perform a hop-by-hop check. Next, let's see how the SRH changes during the forwarding process. G-SRv6 extends only the format of a SID that can be carried in an SRH. It does not change the definitions of the original fields in a standard SRH. In this example, PE1 compresses SIDs that have the same prefix. The first SID to be copied to the DA field must be a complete SID, which is used to store the prefix of GSIDs. The complete SID content can be obtained by updating the subsequent GSIDs. After detecting that a SID carries the COC flavor, P1 keeps the prefix unchanged, sets the SI value to 3, and obtains the GSID value 3:33 based on the SL and SI values. Then, P1 copies 3:33 to the corresponding position in the DA field, adds the SI value to the DA field to identify the position of the GSID, and forwards the packet. The SI field is located in the least significant 2 bits of the DA field to identify the position of a GSID in the GSID container. The initial SI value is calculated by dividing 32 into 128, and then subtracting 1. The SI value is an integer ranging from 0 to 3. When P2 receives the packet, the SI value is greater than 0. As such, P2 decrements the SI value to 2, obtains the GSID value 4:45 based on the SL and SI values, and updates the DA field based on the GSID and SI value. After receiving the packet, PE2 decrements the SI value to 1, and therefore obtains the GSID 0. This indicates that the compression of the 128-bit segment list is complete. As such, PE2 decrements the SL value by 1. Because PE2 detects that the SID 2001:DB8:100:4:0:1:0:22 does not carry the COC flavor, the SI value is set to 0. Finally, PE2 copies the 128-bit SID to the DA field. To ensure compatibility with non-compression SRHs, GSIDs are orchestrated in 128-bit alignment mode. This means that each 128-bit container needs to accommodate 4 32-bit GSIDs. If the total length of GSIDs in a GSID container is less than 128 bits, zeros are used to pad it to 128 bits. Finally, let's look at the compression efficiency of G-SRv6. The table provides information about compression SRH lengths. We can see that the compression efficiency is not significantly improved on simple networks. In this example, there are 3 end-SIDs before compression. After compression is performed, the SRH length equals the length of 2 end-SIDs. In this case, the SRH contains a complete end-SID, 2 GSIDs, and 2 all-zero SIDs. A network with more nodes participating in compression indicates a longer SRH and a more significant SRH compression effect. That's all about G-SRv6. Thank you for watching. Goodbye.